inside every battery or dry cell, it is the chemical reaction that provides energy to produce a charge separation. If the two electrodes are then connected with a conductor and a bulb, the result is a simple electric circuit in which a flow of electrons occurs. The chemical energy stored in the dry cell is transformed into heat and light. We can also represent the dry cell like this. The electrical charge flows past a specific point in the circuit at a particular rate. This is called current and is measured in amperes. Since electrons are so very small, charge is measured in coulombs. A single coulomb of negative charge consists of 6.25 times 10 to the power of 18 electrons. When 1 coulomb of charge passes a specific point in the circuit, each second, the current is 1 ampere. Current, however, isn't the only important characteristic of a circuit. You can see that the current flowing through both bulbs is the same. Yet, one bulb is glowing more brightly than the other. That means that in the circuit with the brighter bulb, each coulomb of charge must transfer more energy to the bulb compared to a coulomb in the circuit with the dimmer bulb. To understand how this is possible, let's consider a comparison. Suppose a lone skier allows a lift to convey him to the top of the slope. In doing so, he acquires what we call gravitational potential energy. But what if he makes a wrong turn and ends falling off the edge of a cliff? When the skier leaves the edge of the cliff, the gravitational potential energy he gained in rising to the top is converted to kinetic energy as he falls to the snow below. The skier himself doesn't change as this energy transformation occurs. In actual fact, the gravitational potential energy we have assigned to him is made possible by his position relative to the Earth beneath. If the Earth were to disappear, he would not have that gravitational potential energy and would therefore not have to worry about falling. But the Earth doesn't disappear. So, what about the end of the fall? What has happened to the energy? The energy has been used to do work to compact the snow in the drift. Now, suppose that instead of a single skier, there are a number of skiers. As it was before, as each individual skier moves up the slope, he gains gravitational potential energy. This time, however, each skier comes down more sensibly. The gravitational potential energy is only partly transferred to kinetic energy. Most of the potential energy is depleted to do the work of throwing aside the snow. As we watch this cycle, we can see that energy is being transferred from the ski lift motor to the skiers, who in turn transfer it to the snow. Now we can view an electrical circuit in the same way. Instead of a ski lift, we have a source of electrical current, such as a dry cell. Instead of a slope, let's use a length of heating element from a device like a toaster, connected to the dry cell by wires. Instead of skiers, we have coulombs of charge that are going around the circuit. Just as a ski lift gives each skier gravitational potential energy, the chemical energy in the cell gives each coulomb of charge some electrical potential energy. The gravitational potential energy of the skiers was used up moving snow down the slope. As the charge flows through the heating element, the electrical potential energy is converted to heat. At the top and bottom of the slope, a skier may often glide without losing potential energy. Similarly, the connecting wires are chosen to allow coulombs of charge to pass through, with little loss of electrical potential energy. Now, consider 1 coulomb of charge. The amount of electrical potential energy this coulomb loses as it flows through the element from A to B is significant. The potential difference is the amount of potential energy lost by each coulomb of charge between A and B, often stated as the potential difference across AB. Potential difference is measured in volts and is given the symbol V. Potential difference is equal to the energy in joules transferred by each coulomb of charge. Suppose in this example we find that 3 coulombs of charge flowing through the heating element cause the element to give off 4.5 joules of heat energy. We can calculate the potential difference between A and B using our equation. So, in this circuit, each coulomb of charge loses 1.5 joules of energy as it flows from A to B. Since potential difference is measured in volts, we can say that the potential difference across AB is 1.5 volts. The potential difference in volts can be measured between any 2 points, such as these, or these. If the wires DA and CB are good conductors, there is no potential difference between D and A or C and B. Just as skiers return to the ski toe to increase their gravitational potential energy, the charge returns to the dry cell and increases its electrical potential energy. Each coulomb, which lost 1.5 joules of energy in flowing through the heating element, will gain 1.5 joules of energy as it flows through the dry cell. The potential difference across the dry cell is also 1.5 volts. Although here it is an increase in potential compared to a decrease in potential across the heating element. Recall those 2 circuits we saw earlier? The rate of charge flow through the 2 circuits was the same, but the potential difference across the bright bulb was higher. Why does the one bulb require a higher potential difference to produce the same current flow? It must have something to do with the nature of the bulb itself, and we'll investigate this property in the next program.